All right, sorry about the interruption earlier. Okay, so what I was talking was, okay, if you have an object, okay, if you know the center of mass, okay, most you try to rotate it. It's easier when you try to rotate it through the center of mass. However, if the pivot point is shifted, okay, you can use the parallel axis theorem. So for in order to do that, you have to know the center of mass of an uh, inertia of the center of mass of that particular object. Okay, in this case, let's say the pivot point is shifted from O to P. Okay, you draw a parallel line. Okay, and then distance between them, which is h. Okay, the same formula here again. Okay, so let's try to find the inertia, moment of inertia uh, for this object B. Uh, so in this case, okay, you know the center of mass. Okay, if you know the center of mass of a rod, okay, in this case, it has been shifted. The rotation axis has been shifted to this edge here. Okay, so to find the inertia for this, okay, okay, I would be I is summation of MIRI squared. Okay, in this case, I would be, okay, this is what I'm trying to do here. So not using the parallel axis theorem. Okay, so not using the parallel axis theorem, so it will be summation of MIRI squared. So the first mass M, R is 0 because this is located at the pivot point itself. So 0 squared M times L squared, so that gives you ML squared. Yeah. So if you use the parallel axis theorem, so I would be I center of mass plus mh squared. So that we know the I center of mass, that is of the thin rod, that is ml squared, plus the total mass is 2m. Okay, from the center of mass to that is L over 2. Okay, that gives you, so ml squared, the same thing. So this is how we got this I center of mass. Let's calculate this I center of mass. So first mass, okay, is located at negative L over 2 squared. Okay, that's the location. Plus the second mass, which is M, L over 2 squared. That gives you 1/2 ml squared. Okay. So if you have a mass which is continuous, right? Like if you're not talking about a point object, in that case you can use the integral form. Okay, in that case, that change in m tends to 0. That means r squared dm. Okay, here we'll be calculating. So in this case, a thin rod is given, where thin rod, like if you rotate through the center, inertia is 1/2 ml squared, but like if you rotate through the edge, that is 1/3 ml squared. You can see if you shift the center of axis of rotation, then inertia increases. Okay, let's verify this. Okay, let's say you have this rod of length L. Yeah, so let's find I center of mass. This is my center, like I'm rotating through the center, 0. This would be L over 2. Okay, the length from here to here is L over 2. Yeah, so if I take a small portion of this, yeah, let's say I take the small portion, that is dx. Okay, that means this small portion is a small portion of the mass, so that is dm. So I is given as integral of r squared dm. right? So dm over dx is m over L, so that implies dx. So now the previous thing we did here, yeah, here in this case it looked like when we used parallel axis theorem it looked more complicated, but that's not the case for most scenarios, because if you use parallel axis theorem, like you don't have to do a lot of like if you know the center of mass, you don't have to repeat the integral again. So in this case, that will be your x squared, okay, length x squared, m over L dx, negative L over 2 to L over 2. That gives, taking the integral, you get x cubed over 3, negative L over 2 to L over 2. So you bring the constants out, m over L, so it's out of there. So I'm gonna bring m over 3L out, so that gives you L over 2 cubed. So that gives me L cubed 8 plus L cubed 8. Yeah. So 8 over 8, so, sorry, that should have been 4. Oh, wait a minute. What did I do here? Four. This becomes squared, so m L squared over 12. Okay. I equals to I through the center of mass of that rod was ml squared over 12. Now we will use the parallel axis theorem if we move the axis to this edge here. Okay, parallel axis. So I equals to I center of mass plus mh squared, which is I center of mass is m over ml squared over 12 plus h was L over 2. Okay, so that gives you 1/3 ml squared. Yeah, same thing. Yeah, using the parallel axis theorem. So moment of inertia is different for different objects. For the solid cylindrical cylinder or disk, it's 1/2 mr squared. Hoop, shell, or ring, that is mr squared. You can see hoop has higher inertia than the disk. Okay, for different objects, all of these are given to you here, and these will be provided to you for your finals. Yeah, you don't need to memorize these. Yeah. So as you can see in this diagram, like smaller moment of inertia, that means it's easier to spin. Larger moment of inertia, it's harder to spin. Yeah. So which dumbbell has a larger moment of inertia about midpoint of the rod? The connecting rod is massless. So if you consider a rod to be massless, which one has a higher moment of inertia? Okay. So let's calculate that. I, for I in this case is, this is R, so R over 2 m r squared over 4 plus m r squared over 4, that is 1/2 mr squared. In this case, this distance is r from the center, r, so I equals to m over 2 right? R squared plus m over 2 r squared, that gives you mr squared. This one, dumbbell B, even though masses are less, since the mass distribution is far away from the center, yeah, dumbbell B has higher inertia. Okay. So here is an example. Okay, a triangular shape is made from identical balls, and identical rigid massless rods are shown. The moment of inertia about A, B, and C axis. Which of the following ordering is correct if you rotate around A, B, and C? So let's consider this to be 1 meters. Okay. So I, if you rotate around B, okay, and C or A, okay. So if you rotate around A, IA is summation MIRI squared. That is shown here. Okay. So around A here. Okay. So the first mass, which is 2 kilograms, right? R is 0. The second mass, which is 2, okay, that distance from here to here is 2, okay. I'm taking the linear distance here, so 2 squared, 2 squared, which gives me 16 kilogram meter squared. Similarly, if I do for I around B, that gives you MI squared plus M2R2 squared plus M3R3 squared. So that would be 2 times distance is 1, so 1 squared is 1. Same thing, 2 times 1 squared plus 2 times 1 squared, so that gives you 6 kilograms meter squared. I around C is M2R2 squared plus M3R3 squared plus M1R1 squared. So both of this R2 is 0 here, so this is 0 plus 0 plus M1, that is 2 times 2 squared, that gives you 8 kilograms meter squared. So the ordering would be IA is greater than IC, which is greater than IB. Okay. This would be your correct answer. Okay. So now in terms of kinetic energy, so when objects are rotating, objects does not have the rotational, sorry, the rotation translational kinetic energy. It has rotational as well. So you would have to include rotational and translational. So translational, K is 1/2 mv squared. Rotational is 1/2 I omega squared. I will be showing you the detail in the next video. Okay.